We're going to have a talk today by Lawrence Crowl, who's very involved in standardizing C++ in the push for the C++ OX standard. He's going to be talking about some of the new features that are coming up in the C++ standard. He's going to be building on the talk that Matt Ostern gave a couple of weeks ago. And here he is.
Thank you. Am I live? Yep, okay. The first thing I want to clarify is what the standard is trying to do. Extend the language in a new domain so that application areas that were formerly not standard and difficult would be, you could write portable programs for. Enable programmers to write better programs and to try and preserve some source level compatibility. The one thing you will not see on this list is fix the language. Because, as it turns out, that if you have your pet peeve and you try and fix it and you follow that through, you often end up breaking significant source compatibility or breaking the way people want to write programs. So fixing is very difficult. Now, the standard is trying to do that, but in some cases, if it promotes these other two goals, but other than that, we're pretty much not trying to change what's there. This talk, I'm going to try and hit the 6 major primary features that are in this next C++ standard, go over those in outline. So this is not a detail, this is an outline. And then I'm going to sort of skim over the rest of the features and give you an idea of where they are not in the standard in terms of likelihood. Most talks don't have a whole slide related to disclaimers, but I'm going to give it to you. One is, most of this talk is a lie, and what isn't a lie will be a lie later when they change the standard. So, what I want you to take away from this talk is the kinds of things that are happening and a checklist of things you might want to investigate further. And because there's a lot to go through, I'm going to ask that you hold questions to the end unless it's a clarification for what's on the slide. So questions about, did you think of doing it this other way, or that's pretty stupid, or things like that. I'm happy to take those questions, but let's move them towards the end of the talk so that I can keep moving through. Now we move into the first part of the talk. These are the primary features. Everybody really wants these features in the language. The question is how to make it happen. And we believe that these features have a high impact on the way people write programs. So for those two respects, it's pretty important to pay attention to these features. The first main feature, and the one that I've been spending most of my time on, is concurrency. And increasingly over the last few years, we've lost the video. The need has become apparent for some sort of standard mechanism for concurrency. People have been getting by with p-threads and Windows threads and various other platform-specific mechanisms, in large part because not many applications get hit by it. They tend to get hit in rather small areas, and so you can survive. However, with the advent of more and more client-server programming and the introduction of multi-core processors, parallelism is going to be everywhere. We need the language to have a standard way to talk about all of that so that people can write portable concurrent programs. The main thing we're doing is standardizing the current environment. There are a lot of good ideas for parallel programming. They're all over the map, and everybody has ideas of why theirs is better. And it's probably true, but we can't afford to chase what isn't well supported by the operating systems. And in fact, we're going to hew fairly closely to what's actually there in the operating system. The approach of the committee can be broken into 2 parts. There's the core language part and there's the library part. The core language part is really focused on what does it mean to share memory and how are your variables different. This is the kind of detail people just sort of assumed would be there, but that's because you're assuming a sort of a model of shared memory that's no longer practical in the real world. Then at the library layer, there's lots of questions about how things happen and where things get hooked up. And so there's still ongoing debate in a lot of this area. The first thing about the memory that we're going to be dealing with is that we have a loosely coupled shared memory in the wild. That's the way the machines work. The traditional notion of, you do a write to a variable and every other thread sees it instantly is no longer viable. The hardware doesn't work that way. So we need to export the complexity of that model a bit through the language. And we do that by basically, if you have normal reads and writes, those are local to your thread until they're explicitly communicated to other threads. And we don't use volatile to make that happen. The problem is volatile has existing semantics, and we might start breaking things if we messed with those semantics. Now, the other effect of this loosely coupled thing is that what happens when two threads try and do ordinary writes to the same variable concurrently? Well, this is called a race condition. It means your program is undefined, and it could as well order pizza as do what you asked. So, but we define what races are, and I won't go into that in the talk. A consequence of all of this definition, though, is that some optimizations in the compiler are no longer legal. So the back ends of the compilers will have to change. We don't believe that these optimizations are important or significant, so we're okay with restricting those optimizations. On the other hand, there are a number of optimizations that key off of an assumption that loops will terminate, and those are important. So we're basically going to define a priori that the compiler may assume that a loop will terminate. And this affects code motion significantly. So there's sort of a compromise between the optimization and the strict program. The next topic is variables. What happens to variables in a concurrent world? Now, you might have thought that this was already handled by the previous slide of what does it mean for memory. But in fact, it's not quite. The first thing we'll be doing is adding thread local storage. This is in a lot of compilers already, and we're pretty much going to standardize the common existing syntax. But unlike the current implementations, we will probably also allow for non-pods, that is, constructors and destructors on thread local variables. So this gives a whole new storage dimension to the language. The next thing we need to deal with is what happens when you have multiple threads that try to initialize a variable at the same time. So for function local statics, we will synchronize that in all likelihood. For global variables, we'll probably rearrange things so that what is currently barely reliable becomes illegal. And that then allows concurrent construction of global variables. And you have the whole issue of destruction of global variables. Exactly how does that occur? And should you do it at all? Should we take a major incompatibility hit and say global variables are never destructed? There's some good reasons for that, but source level compatibility is a severe constraint. Maybe we don't want to break programs quite so much. That is still an open debate. I'm happy to hear opinions on that. Moving into the library side, our first steps into this are going to be somewhat conservative. We'll have a basic thread class that has a fork and join model of execution, and not much more. And then with some hooks to get to OS types. So if you really need to use POSIX details on your thread, you will be able to get the POSIX handle for the C++ thread and tweak it. And our hope is that that will be confined to those applications that are serious about it and in areas of the application that are already somewhat machine dependent. But that the bulk of the language, the bulk of the program, will be able to work without this. The synchronization model is mutexes and condition variables, which is common in the POSIX world, and it's cropping up in the Windows world. The primary reason to go this route is everybody who's programmed in both models agrees that the condition variables are easier to use than the Windows events. And it allows the monitor paradigm, which has some theoretical work behind it. Termination, when a thread ends, is where some of the sticky stuff starts to come in. The easiest case is when a thread just exits its top level function. So the thread is done and continue on. What happens if that's not the case, that you want a thread to die earlier than it otherwise would have? In that case, the standard is going towards some form of cooperative termination, where the thread you want to die has to cooperate. And the reason is that any non-cooperative way involves some sort of asynchronous hit to the thread. And that asynchronous hit causes immense problems in the language and the compiler. And there's strong opposition against that. Then the question is, well, what happens if the thread throws an exception and it's never caught and it goes off the top? And the answer is, well, there are several answers, and the committee is hotly debating this issue. So I don't want to try and predict what's going to happen out of that right now. Now, the plan, however, is to do significantly more later, if not in the standard, than in what's being called TR2, Technical Report 2. This is a library technical report. And the intent is to simplify a lot of the kinds of programming that people are going to want to use routinely. Thread pools, values with joins, futures, parallel iterators, all kinds of stuff. The reasons for deferring this work sort of add up. And I don't want to there's no one reason you can point out, but there's a lot of little reasons. The next major feature is called concepts. Think of this as type checking for templates. So right now, when you write a template, you really have no way to communicate in the language what it requires out of the parameter types. And anybody who's done the wrong thing with a template has noticed a 2-page error message, and you have to try and figure out what went wrong. And so this proposal is intended to address this issue. It also has a consequence in the way people write generic templates. So what we're going to do is add in a construct called a concept. And when you write a template, you can say, this template requires this concept on its arguments. In this particular case, we can say the combination of parameters I and V must meet the concept or the constraints of an input iterator. And then you continue on with the definition of the template. Yes? Excuse me? Yeah, that's an exclamation point. Let's defer that till later, okay? So we have templates, we have concepts, and how do you write a concept? Well, a concept looks very much like a template. The only difference is that the contents of the concept are basically a signature of the operations that you need to apply. And these operations don't necessarily have to be member functions. They could be free functions. But those signatures sort of have to exist so that the template that uses them can be assured that it's available at the time when the person writes the template. So right now, when you write a template, there's no real type checking until it's off in the user's hands. With concepts, you'll be able to check ahead of time at the point where you write the template before you ever give it any client type, any parameter type. As you might suspect, you can compose these requirements, these concepts into, build upon previous concepts. Now, there's this little keyword up there called auto. And that is because of a third notion in concepts, and that's the concept map. So if you have concepts and you have types, how do you connect the two? Now, for auto, that handles the case where the two have an obvious mapping. All of the function signatures are exactly the same, the names are the same, everything just maps straight over. And the compiler will do that automatically if you have an auto. If things don't map up automatically, then you can write a concept map manually, and that allows you to do things like map a concept into a pointer. So an iterator, in the current standard, pointers can serve as iterators. But you need a way to make sure that the pointer matches the signatures of a concept. And so that's where that map comes in. So you want to think of this work as three pieces: the template, the concepts it requires, and the mapping between concepts and types. The next major feature technically is called rvalue references. But more generically, you want to think of this as move semantics. And what it's trying to do is address a problem with the way people write C++ now, in that the natural way to write a number of things results in a lot of copying. And as objects get bigger and you pass more and more parameters, this can result in substantially more copying. And you often really don't need the copying, and sometimes it's wrong, like when you have a lock or certain other things like that. And so we'd like to be able to write code in which we don't copy things, but instead we have a conceptual move of the information from one variable to another. Not a copy of the information, but a move of the information. The information is drained from the old object. In some ways, you can think of this as doing for copying what mutable did for const. It gives you a way to sort of back through excessive constraints. And as I mentioned, the rvalue references are the mechanism we use to achieve the move semantics. Basically, it's a new kind of reference that will also bind to values as well as variables. And we use this double ampersand as a declarator to make that happen. And like regular references, they aren't first-class types. They're sort of an abbreviation within the type system to allow you to write things. And in the example down below, you can see where you would sort of have a difference between the existing copy semantics, where we do a copy construction, and the move semantics, where we sort of copy the pointer over and eliminate the pointer from the other side. And that's the difference between the move semantics and the copy semantics. Sort of the classic example of where this move semantics helps out is in swap. If you write swap in the ordinary way now, everything ends up with two copies at one point or another. So you've got 3 full copy operations in extra storage. With move semantics, you can eliminate all those copies and just do the moves. And that syntax there, std::move, is a function in the library that does the appropriate implicit casts to make that happen. So that's not a language primitive. It's just an auxiliary function in the library. But you can expect to see that show up in a lot of code. And you can also use it for forwarding. In particular, if you want to create a factory, the typical implementation of a factory ends up copying the arguments yet again. This allows you to just sort of chunk those arguments straight through. The next thing we have is constant expressions in the language. So right now we have constant expressions, but they're really confined to basic type, basic operators, and anything else isn't constant. The problem we have is that particularly within the context of template programming, you really want sort of a generic facility for constants. So macros don't work well in templates, and if the standard defines the numeric limits that everybody knows it's constant, but because of the definition of language, it's not constant. And that's a bit of a problem. The fact that certain types aren't constant and certain expressions aren't constant means that the standard library is sort of written with vague words where everybody knows how they want to implement it, but they don't really want to standardize the sort of quirky way it's implemented. So there's sort of notional types that are manifest as either an enum or an int or something like that. But probably the most important reason is user-defined literals. People would like to write their own type for, say, a probability and be able to write a user-defined compile-time literal that could potentially get baked into ROM. There's no way to do that in the current language. And this mechanism lets you do that. So here's the simple syntax. We've introduced a new keyword, constexpr, and you can provide that as a function specifier, and that says the intent here is that if the argument to this function were a constant, then the function itself would be a constant. And the way there's a syntactic restriction that the body of the function must be a single return statement with a constant expression. So the compiler can validate that you are correct by assuming that arg is a constant and then seeing if the return expression matches all of the rules for constant expressions in the language. And if it doesn't, it will provide a compiler error. But you're not restricted to using this function on constant arguments. You can use it on variable arguments, but the resulting function call won't itself be a constant expression. So we can push that through, but you might get silent place in your expression where the constantness of it has been dropped. And you can prevent that by declaring a variable to be a const expression. And that says, I expect this to be constant. Warn me if it isn't. And it all follows through. And the bottom case is where that has failed to happen, where we get an error because beta is a variable, it's not a constant. And so that stops us as we move on through. And here's where the user-defined literals show up, in this case for complex numbers. We're basically going to run through and make all of the member functions be constant expressions so that we can write a fairly hairy expression and have that come through as a constant available and evaluated at compile time. And in this case, we're doing what the library would do for us, which is declaring a constant for the unit imaginary. And all of that can work with general purpose language mechanisms. We have had no need, in this case, to introduce complex as a predefined language type to get compile time efficiency out of the type. So we're leveraging a general purpose feature, and you as regular programmers can also leverage this feature. The next big feature we have is, you had a clarification?
Yeah. Is constexpr actually ever changing what the compiler would generate, or is it just generating warnings if you violate what you're saying you're going to do?
it will change what the compiler generates. The next major feature we have is automatic typing for variables. So the compiler right now does an awful lot of type inference in the process of doing an expression. But the minute you write a variable declaration, you have to be very explicit about the type. And so this is a way to avoid having to dredge up type information in places where you don't really want it. And in particular in refactoring. If you have the top expression, you're looking at doing some investigation to see what the type is and how to declare any variable if you want to avoid doing the duplicate call. And now with reusing a very old C keyword, we can make that happen automatically for you. That helps when you're declaring variables, but we can also get information from expressions, which helps template writers avoid having to ask more information out of the user than necessary. In particular, if I'm trying to write a product function, right now, if T and U are of different types and perhaps the product yields a third type, I have to ask for all three types out of the user in order for them to be able to call my function. You really want to avoid that extra type information because you can infer it. And we're basically using something very similar to the GCC type of primitive. The names have been changed to protect the innocent. And so now you can write the declaration of product in terms of the type of an expression rather than asking for information to come in. However, what I just told you was wrong. That code was wrong. And the problem is that T and U in that decal type are not yet in scope. And we certainly don't want compilers to have to try and sort of vaguely skip over the return type and get back to it later. So there's a new syntax that moves the return type for a function to after you've parsed the parameters, and now that decal type can work. The next major feature of the C++ language is garbage collection. The reason is that memory management can be hard, and one of the main criticisms people levy at C++ in comparison to, say, Java, C#, Python, is that I have to put in these delete operators at the right place, at the right time. So for some applications, that's a problem. For other applications, having to do that results in better efficiency. And so the C++ committee would like to make both possible. You can sort of do that right now with conservative garbage collectors, but not always. And to do better than conservative garbage collectors requires language support, which is the current standards effort. Conservative garbage collectors are based on the principle that if the bits look like they could be pointing to a real object, we will assume they will. So if you have an int whose bit pattern happens to match that of a pointer somewhere else, then it's a pointer, by God. Now, this almost works today. There are just a few situations which people almost never do for which it doesn't work. We could theoretically just outlaw those cases and say use a conservative garbage collector. But we're not quite ready to go there. So for those people that really need these kinds of hacks, there's a way to do it by saying that garbage collection is forbidden. And likewise, when you start writing programs that don't do delete operators, now you suddenly have an application that really needs garbage collection, and so now you say it's required. If you ever have a program that has both forbidden and required in it, that should result in an error at link time. And so in the medium term, you should write your code assuming neither of those things. So you still want to put in the delete operator, but don't try and go off into the weeds with this other stuff. The default is neither. So the intent is that whoever does the final link line gets to choose. So this mostly affects library writers who have to be very careful to make sure that they don't wander. But if you are writing the final application, then you can pretty much do whatever you want, and it'll show up. But if you're writing a library, be very careful to make assumptions. But to do better than conservative garbage collection, you need a little bit more information. Some applications have a lot of random bit patterns, and the garbage collector wandering over that will pretty much think everything's in use and never collect any garbage. So we have a way to specify for any given type that you can believe the types in this, right? We won't be casting this type to void star and you know, casting it to int or anything like that. So you can pretty much believe the type system, and the garbage collector can then take advantage of that information. And mixing these two things is supported. So this gives you a way, once you've decided to get into garbage collection, it gives you a way to sort of cooperate between type-safe and conservative garbage collection. When you go to the type-safe garbage collection, you suddenly do start getting into some limitations. One of which is that your own allocators interfere, because there's more information that needs to be communicated from the program to the memory allocator than the current functions can support. And so without a mechanism to communicate that information, it's not going to work. And right now there's no sort of finalization facility. And maybe there will be, and maybe there won't. So that's it for the major features. And I know I've been sort of breezing through this at lightning speed. But there's a lot of other features we're going into. And these features have varying status. So your favorite feature might not make it, and it'll show up on this list, possibly. And for those of you that are color challenged, you want to pay careful attention to the bullet. The shape is different depending upon the status. I particularly want to highlight the bottom one, which is deferred to technical report work. What this means is that it won't be in the next C++ standard, but it may be in a technical report, which is sort of an optional part of the standard. Or people may do a bunch of work on it and decide it's not even going to make it that way. So this is sort of deferred work, maybe, maybe not, but certainly not now, as opposed to the second item there, which is maybe, maybe not, but we're working on it to try and make it for the next standard. One that's important for many of the current applications is Unicode support. The basic characters type is probably going to make it in. And the reason we have to sort of do anything in the standard is that the current language leaves the basics of characters pretty much to be platform dependent. So if you're writing a library for general use, you look at those characters and you say, I can't use these because they're variable, they're too platform dependent. So this is a way to provide some solid ground for library writers. And then there's some follow-up work to enhance and make that come through. There are more template features. The big one that often bites people is putting two right angles and having the compiler report that this shift operator doesn't make sense here. And in fact, this feature has already been implemented in GCC and might make it out to you within a release or two. Variadic templates, explicit instantiations, template aliases, they're sort of like type def for templates. Some of the types in the language are excessively weak for what people would like to do. Enums will fall apart into an int on the first hint of danger, and sometimes you don't want that at all. And then sometimes you'd like to have a type that has all the operations of an int, but isn't really an int because you want to overload on it. And so there's work on that as well. There's a fair amount of work trying to generalize classes. So right now, classes work generally fairly well, but there are some weaknesses, particularly with constructors. So you have to repeat a lot of constructors where you would like to factor out some common code. Initialization in a couple areas is kind of obscure and unclear. For those of you who were here a couple of weeks ago, Bjarne Strostrup talked about initializer lists and unifying the way you initialize variables, so you can have that be more general. There's proposals right now. There's sort of, full classes and plain old data, and there's this sort of big gap between them, and you either are or you aren't, and sometimes that requires restrictions that aren't really there. So let's relax those. Controls of defaults, forwarding constructors to base classes or to other constructors, work on all of those. Likewise, identifier lookup and access to members is a bit difficult right now. It's been extended in a couple areas, and there's existing work on others of those. Explicit virtual overrides means if you have a base class with a bunch of virtual functions and you want to add in one more virtual function into the override mix, well, in a derived class, well, you can't do that because adding in one function creates a new scope, and you only have that one function unless you go through and you write all those functions and then call the parent one. So you end up having to create a lot of functions where you would rather not. Argument-dependent lookup, if you don't know what that means, well, there's some problems with it, and we're trying to fix it. The next thing is C99 compatibility. The C++ standard was formally adopted in 1998, finalized in 1997, which was before the C standard was finalized. And this is sort of playing catch-up. Several of the features of C99 have come forward, primarily long integer types and the C99 library, and most importantly from those people that write header files is preprocessor synchronization. So the C++ preprocessor and the C preprocessor are exactly the same, and you can rely on that. There's other things that happened in C99 that are not coming forward into the C++ standard. Compound literals are not coming forward. They have L-value semantics, which sort of wreaks havoc in many places in the C++ for use in C++. Variable length arrays have semantics that don't work well with C++. Designated initializers, they don't seem to work very well with C++. Hexadecimal floating point, no one's been pushing it, so there's no big push for that. We have some new control constructs we're working on. Probably closest to adoption is some flavor of for each loop, which allows you to not have to set up an iteration variable. You can just say, here's the data structure, I want to walk through it. The next two bullets fall under the general category of lambda or closures. The problem is that people mean different things when they say those words. And the primary two use cases of this, anonymous nested functions, sort of like Pascal, but allowing you to write certain kinds of parallel code directly and efficiently. Scope capturing closures for people that want to sort of defer computations till later. These are really two different use cases, and they need different language support. The problem is how to make those happen in a way that doesn't interfere with the rest of the language. There is something called Technical Report 1 after the first standard, several years after the first standard. The library subgroup of the committee issued Technical Report 1, which was things we think are a good idea, go ahead and think about putting these in. Those have been formally adopted into the next C++ standard, and you can look for them. And I'm going to highlight some of those. One is function objects, so that you can manipulate things that look like functions as data. There's also been several proposals for things that affect how you talk with the rest of the system. In particular, alignment of variables and types so that you can talk with system-defined things. Probably the biggest example right now is some of the SIMD instructions on the Pentium SSE. They require 16-byte alignment, which isn't natural for some of the operations. There's libraries to deal with file systems, networking, and shared memory. There's proposals for C++ modules that try to do some more of the typing and scoping more aggressively ahead of time. That work has been deferred to a technical report. There's a significantly less ambitious proposal to support dynamic libraries. That proposal is iffy. Everybody's been using assert.h macros for quite a while. The question is, can we do better than that? Static assert does those kinds of things at compile time so that you'll get a compile time warning if you fail to meet those. A significantly more aggressive proposal for contract programming or function preconditions is not going to make the standard, may make a technical report. There are some additions to the standard library to help you manage data. In particular, a major somewhat embarrassment from the first standard is that the next standard will have hash tables. It will have fixed size arrays. Think of this as the C++ counterpart to variable length arrays. There are tuples, better smart pointers, and reference wrappers. There's been significant work for numeric facilities. There's a random number generator library that's in the first technical report. There's also work on interval arithmetic, special math functions, some other topics for technical reports, decimal floating point. And this is where, not that the literals are written with decimal digits, but that the actual runtime representation is decimal. And this is important for various accounting practices where the law says that you will round with decimal semantics. And so people writing such accounting applications really do need to do decimal, and this helps them out. Infinite precision integer library. And then there's a bunch of miscellaneous features which I couldn't actually categorize. Type traits allows you in a template, when you're doing template metaprogramming, to say, is this type an X or is this type a Y? There's a regular expression library. Think of it as very similar to some of the regular expression libraries that are available on Unix. There's a new way to write null pointers instead of the C hack of using 0 and hope it gets interpreted as a pointer in the right contexts. There's a proposal for multi-valued logic. And there's something called raw string literals, which is available in some other languages. So the problem is, if you are embedding one language in another, and they use backslashes to quote, and C++ uses backslashes to quote, you start getting into this exponential decay of backslashes and quotes and so forth. And having written such code, it can take weeks to get the number of backslashes right. So this bypasses all of that. So you basically have a prefix where you can say, ignore everything until you find this matching prefix at the end. And the best place to go for more information is the C++ website. And here's the links you click on. And this N2142, that is the paper number for a paper describing the current status of evolution of the various concepts. So you go to that paper, you start looking around for what you're interested in. That will refer to you to other papers, and you can start doing more investigation. The other thing you can do is ask questions of those of us that are working on the C++ standard, and we will try to help you. And in fact, now would be a good time to ask those questions. Yes?
Two questions. First, you mentioned a new facility for when you're trying to infer the return type of a function, where you declared it like function name args and then arrow something. Is that facility also available for just returning normal non-inferred types? So I could decide to declare all my functions that way if I like, or is that only for inferred types?
So the question is putting the return value at the end supported for regular types instead of just inferred types? And the answer to that is yes. Here we go. That's the example. Yes, you can use any type there. We don't want to unnecessarily restrict these things. So the C++ committee is working hard to try and make sure that the mechanisms apply as broadly as possible. So we will throw out mechanisms in the standard process that do not work well inside of a template. And once it works in a template, there's no reason to not have it work outside of the template as well. Template metaprogramming and data structures and stuff, people are writing and relying on a lot of that, and special cases just do not work well in that environment.
Okay, second question that I had was, you mentioned later in the garbage collection section that there was a way to tell the compiler to be very strict about assuming that when you say you have an int type, you really mean you have an int, and you're not going to do things like cast void stars around. When you declare that sort of thing, can the compiler also check for you that you're not actually doing those sorts of casts and then complain if you are?
Okay, the question was, can the compiler check here when you have said that a certain class is type safe? And so the way this works is that the runtime garbage collector will, if you have, say, a struct, and one of the fields of a struct is an int, it will believe you when you say that that is an int, and it will not look at those bits for a pointer. So it will only look at the fields that have been declared to be pointers. So in that sense, the compiler really can't check at that point what's going on. What you're asking is that in combination with the compiler checking to see if you're being strict with the use of the types as the C++ language defines them. And this proposal is not trying to do that, but there is work among the various compilers to try and detect those issues. And there are people working here at Google on that issue, so that we warn people about misusing the type system that way. And the reason that's going on now, independent of garbage collection, is that it affects optimization. So we can do a better job optimizing programs if people play strict with the types. And so we want people to know when they're not doing that. So independent of the garbage collection issue, you will find more and more compilers trying to help you avoid those kinds of type machinations.
With the automatically inferred function return types, why can't we just use auto?
The question was, with the automatically inferred function return types, why can't we just use auto? The problem is that as a type specifier, the auto doesn't work very well because the function is the type. The return type is part of the function. So what's it going to infer it from? And the second thing is, usually you want this in an environment where you're simply declaring the function, not defining the function. So sort of auto's the wrong place to make that work out well. No more questions? All right, then. We'll call it a wrap. Thank you for coming.